Hello. So today let us see carbocations. So today we are going to discuss all the related concepts with carbocations because it's a very important reaction intermediate and like when we are going through reactions in organic chemistry, we are going to come across carbocation intermediates a lot of times, and we need to judge the stability of the product using the stability of the intermediate. So that's why carbocations and the intermediate topics are very important because they build a base between the reactions and the GOC. So today, let us see carbocations. So carbocations are sort of reactive intermediates where carbon has a positive charge. Okay. So carbon can have positive charge in two ways. So it is already bonded to one hydrogen. Okay. So for example, let's say this carbon is connected to some hydrogen or some metal X. Okay. So for example, the metal X or the element X has left as X minus. So carbon will get C plus. That is one way of getting positive charge. And another way is now the carbon's valency is full, but you are going to force carbon to donate another extra electron. So then it will get a positive charge. Okay. So those are the two ways the carbon gets positive charge. Now those two ways are here down written, that carbenium ion and carbonium ion. So what is carbenium ion? It is tri-coordinated system. Means the carbon is connected to three different alkyl chains or something. It is making three bonds and it has a positive charge. And carbonium ion is pentacoordinated system. Means carbon has already completed its fourth valency, and then the fifth valency is the extra one. Sorry for the disturbance, right? So the fifth valency is the extra one. So such kind of things are called pentacoordinated systems. So those kind of ions are carbonium ions. Now, carbenium ions are six electron systems. So they have six electrons. See, 1, 2, 3, 4, 5, 6. Okay. Carbenes, which comes under free radical, where the carbon has six electrons. Okay, like this. Now, carbonium ions are eight electron systems. Okay, and they are rather unusual ions. It's really rare that carbonium ions are formed in the stages of intermediates, but they form. Okay, but it's really rare. Now, general difference whenever we speak about carbocation, then we speak about only tri-coordinate system or the carbenium ion. Okay, so carbenium ion C plus and three bonds. So what is structure of carbocation? So what is the hybridization of carbon? How do you write hybridization? So we have 1s2, 2s2, 2p2. Okay. So in excited state, one electron jumps here. Okay. So the one electron has jumped here. So we have one s orbital and four p orbitals. I mean three p orbitals. So these all combine to form three. Okay. Four sp2 hybridized molecules. But the catch comes here that carbocation is positively charged. So it does not have one electron. One electron was taken by some other metal. Now it has three uh, orbitals with electrons and one empty orbital. So these three would, these four, okay. So these three would combine to form sp2, s1, p2, and then one p orbital is left empty with carbon. So sp2 is planar geometry. So three sp2 orbitals are formed and one vacant orbital is left with carbon. So it is how something looks like this. So it is CH3 plus structure. Now the carbon has three sp2 hybridized molecules in hybridized orbitals. So which are represented using the red color here, and it has an empty p orbital. Okay, and then these are the overlapping of hydrogen. Hydrogen is s orbital, right? The hydrogen comes and overlaps the sp2 orbital, so CH3. So it is a, we can clearly see it is a sp2 hybridized, which means diagonal planar, and then the p orbital is going to be like this, like this. Okay, it is sp2 hybridized and it's going to be triangle planar. Let's see some classifications in carbocations. So we have 3-degree carbocation, 2-degree carbocation, 1-degree carbocation. Similarly, it is the carbocation is connected to 3 carbon atoms, 2 carbon atoms, and 1 carbon atom. 3-degree, 2-degree, and 1-degree. So another types of carbocations we have are vinyl carbocation. Vinyl is when you have double bond. Okay. So when you have double bond and you are discussing something on the double bonded carbon, that is called vinyl. So we have vinyl carbocation, which means this. Allyl carbocation, which means after vinyl. The next position of vinyl is called allyl. Okay, so this will be the allylic position. And then phenyl, where the positive charge is on the benzene ring. When it is on the benzene ring, it will be phenyl. And benzyl, when it is outside the benzene ring, like this, something like this. It is benzyl carbocation. Okay, so what is stability of carbocations? How do we decide stability in carbocations? We have seen in GOC, so let's summarize it. So you can find stability of carbocations using three factors: the inductive effect, the resonance or mesomeric effect, or the hyperconjugation. So, what is inductive effect? Inductive effect is a permanent displacement. Okay, sorry, it's a temporary displacement. It is caused due to the electronegativity we have seen in GOC. So there are two kinds of inductive effects: plus I effect and minus I effect. So plus I effect is the this group donates electrons to carbon. Minus I effect is it withdraws the electrons. Okay, this is minus I effect. This is the plus I effect. So carbon has positive charge here. Now means it is electron deficient. So when there are plus I groups, means electrons are being donated to carbon. The positive charge gets nullified. So when charge gets nullified, the stability gets decreased. We know from this graph. Okay. So the charge has to be nullified. So plus I effect will increase the stability of carbocation, and minus I effect will decrease the stability of carbocation. That's what here it is written. No. Stability increases by decreasing the positive charge, by nullifying the positive charge. So plus I groups will donate electrons to the carbon plus, and hence this charge is nullified and stability increases. So the first conclusion we reach from inductive effect is 3-degree carbocation is more stable than 2-degree carbocation, is more stable than 1-degree carbocation, more stable than CH3 plus. Why? So CH3 acts as plus I group, so it donates electron. This positive charge is decreasing. So similarly here, 2 are giving electrons, this will decrease. And similarly here 1. So 3 plus I groups, then 2 plus I groups, then 1 plus I group. Okay. So that is the first conclusion. 3-degree carbocation is more stable than 2-degree and more stable than 1-degree. This is stability order. Stability decreasing order. Now, what is minus I effect? So minus I effect means the electrons are being withdrawn. Means first only the carbon is deficient, and again you are pulling electrons. So the charge here will increase. So when the positive charge will increase, the stability will decrease. So that is about inductive effect. Let's see in the case of resonance. So resonance or mesomeric effect, we know that resonance is like delocalization of electrons. We have read all the theory in GOC. Let's see the application. Stability of benzyl carbocations is the application of resonance. Now, these are the benzyl carbocations. Now, when you have two phenyl groups, three phenyl groups, what is happening? So here, I can draw resonating structures like 3 times more than this, right? Like we can clearly see that this has more 3 has more resonating structures than 2 than 1. So when there are more resonating structures, we know that the stability is more. Okay, so that is why, because of extended conjugation and more conjugation and more resonance, more resonating structures, 3 is more stable than 2 is more than 1. So that is how 3-degree benzyl more greater than 2-degree benzyl more than 1-degree benzyl carbocation. More number of resonating structures, more the stability. Very simple. And another important effect of resonance is the stability of allyl carbocations. So how do we decide here? Allyl carbocations. So here resonance is seen because of conjugation. Okay, sorry. And then try to here, right? Right. So because of conjugation, 1-degree allyl, and then because of conjugation, 2-degree allyl, and because of 2-degree allyl. First, here this is managed by inductive effect, and then here you have resonance. Here also it is managed by two inductive effect and then one resonance. So what will be the order you are getting? By conjugation and plus I effect, 3 degree allyl carbocation is more stable than 2 degree allyl carbocation is more stable than 1 degree allyl carbocation. So it is based on allyl groups. Now in benzyl carbocation only, what if you add some other groups to the benzene ring? Like nitrobenzene, you have this OCH3 group and you have normal benzene. How do you see? So plus M groups means plus M groups are electron donating groups. They give electrons. So plus M groups increase the stability of benzyl. They are giving electrons, right? So when they are giving electrons, the plus charge on the C plus will decrease. When the charge is decreasing, stability will increase. And minus I M will decrease. Minus M will decrease the stability because they are withdrawing groups. They pull electrons. So here we have some example. We have NO2 here. We have OCH3 here, and we have normal benzene here. So let's call this structure 1, let's call this structure 2, let's call this structure 3. So NO2 is a minus I group, it will withdraw electrons, so the stability will be the least. Okay, and then 3 and then 2. Why 2 is the greatest? Because OCH3 is a plus M group, it will donate electrons, stability of this benzyl carbocation will increase. Now, hyperconjugation. Hyperconjugation is called no bond resonance or Baker-Nathan effect. So it is like more number of hyperconjugating structures, more stable. Check for alpha hydrogens. Important example. Let's see some important example here. This is a very, very important example. So what is this example is, we are going to compare various carbocations here. Now we have some carbocation with 3 degree, carbocation with 2 degree, carbocation, we have phenyl carbocation, and then we have allyl carbocation, we have benzyl carbocation. 1, 2, 3, 4, 5. Let's tell the stability order here. Now, what will be the most stable among this? Let's first check resonance. So here, whenever you are deciding the stability, resonance is given more priority than hyperconjugation than inductive. So among the following 5 compounds, which has resonance? So I can see conjugation is there in allyl and benzyl. Okay. Yeah. So in phenyl there is no resonance, and in vinyl there is no resonance, and here also there is no resonance. This is not any special carbohydrate; it doesn't have any name. So here also no resonance. So you have resonance among 5 and 4. So here you have more resonance because you can draw more resonating structure for 5. So 5 is the most stable. Okay, and then of course 4 would come because resonance is there. Now among 3, 2, and 1, how do we decide? Now see here. Now, phenyl carbocation, right? Yeah. Here in 3 there is no resonance, right? And then if we are talking about C triple bond C, here what is the hybridization of carbon? sp hybridized means the S character is 50%. When S character is more, the electronegative nature of the carbon is more. See, the electronegativity of carbon is more. So here the electronegativity of carbon is more, which means that it acts like an electronegative carbon, and on this electronegative carbon, you have a positive charge. On electronegative atoms, positive charge is not that preferable. So one will not be the least. Okay. So one will be the least. Among 2 and 3, vinyl carbocations are pretty stable. Okay. So vinyl carbocations are pretty stable than phenyl. Because there is no resonance in both of them. But then also check the hybridization. So here you have 2. So sp2. Here also you have one hydrogen, right? sp3. 1, 2. sp hybridized. Right. So electronegativity is not working here. So among 2 and 3, how do we decide? So phenyl carbocation is less stable than vinyl because vinyl has better reach. So vinyl is more stable than phenyl. Okay. Right. So this will be the order 5, 4, 2, 3, 1. Okay. So it is just a factual point that vinyl carbocation is more stable than phenyl. Now, note here this kind of carbocation means you have three cyclopropanes like this. So here there is a effect called dancing resonance. So that is why these are exceptionally stable than benzyl carbocations. Okay, so these are exceptionally more stable. This is a factual point we have to remember. The reason is dancing resonance. Now, let's see some aromatic carbocations which are more stable because they are aromatic. So we have cyclopropenyl carbocation. We are going to come across these three carbocations a lot. Okay, so we have cyclopentadienyl carbocation, which is also very important, very stable. And then tropylium carbocation, which is very, very important. We have many reactions where this intermediate is formed. So tropylium carbocation is its common name and it is very important like intermediate. So this is about carbocation. We have covered all concepts related to carbocation, right? Thank you.